Okay, so OPAMP is the miniature name of operation amplifier. So what is the operations we are interested in? We should know that in electronic designer, we are trying to design solutions. We are trying to design solutions for the common problems. So usually the solutions involves mathematics, maybe adding, subtracting, dividing, you know, logarithm, exponential, integration, differentiation, all those things. So basically the solutions involve some mathematics, some tricks, some kind of shortcuts or whatever. So we need there are a lot of operations involved. You know what is algorithm? Algorithm is step by step procedure or steps to solve any problem. So all those engineering problems require step by step sequence. So this sequence requires mathematical operations, right? So operation involves all those common operations which we know: addition, subtraction, multiplication, division, you can say integration, differentiation, exponentiation, logarithm, anything or any mathematical operation. So this all has to be implemented in the in your hardware for perfect solving your holistic problems. Uh, for example, you have two voltages, V1 and V2. You need to add them both. Output needs to be add them V1 plus V2, or we have to subtract them V1 minus V2, or we have to multiply them V1 into V2, or divide them V1 divide by V2, or we may have to average them. That's much easier. Averaging is much easier. V1 plus V2 divide by. So these are different operations, right? Or maybe we have to exponent you or logarithm log V1 log v1 or v2 or log v1 plus v2 or any operation. We have to integrate, differentiate, difference v1 dt with respect to time, right? So these are all operations which we are interested in. As an engineer, we have to implement these things. So initially, right now we have a lot of other ways of implementing, maybe digital also, but operation amplifier was used for operations, for mathematical operations, right? So even operations involves analog to digital conversion, ADCs. That means we have analog voltage, we are converting into digital voltage. So this is also an operation, ADC, and reverse operation, digital to analog conversion. We have digital input, and we are converting into some some voltage waveform. So this is called DAC, digital analog. So these are also operations. They are not something different. These are also operations. So these are also used performed using OPAMP. We can use OPAMP for these operations also. Mathematical, uh, all other complicated computations, transformation, conversions, etc., etc. So right now you already know how we does things, because we have discussed in sensor instrumentation, as well as we know we have some signal, analog signal. We can these days we may think, okay, we'll convert to digital using ADCs. Then we can have a digital signal processor or microcontroller, microprocessor, whatever, DSPs. Initially, there may be some amplifier or something. There may be some amplifier, whatever, or filter or kind of thing. Now we use signal processor. We do all kind of digital processing, multiplication. This is what we are just discussing: multiplication, division, addition, subtraction, all those things, integration, differentiation, log, all those things. These days, this is the common solutions. DAC. Now we have a DAC. Now your output comes in the analog form. Same thing, processed output, right? Because here we have in between, we are converted into digital, and the digital output of the DSP, digital signal processor, has been converted into analog form by the DAC, digital to analog converter. DAC, I think everyone is familiar with DAC, digital to analog converter. Whatever the digital waveform or digital pulses you give, it converts corresponding analog waveform. This is with respect to time. This was also just time. This is the voltage, you can see. This is also voltage. So this is analog to digital converter. Analog to digital converter. Okay, fine. Okay, so but we already discussed this is quite a bit slow. Although we may think that digital is very fast and all those things, but contrary to expectations, digital is comparatively very slow. Why? Because of this in between processes, conversion from first we need to convert the analog from digital, analog to digital, then digital to analog again. So these things look a lot of power consumption, a lot of computation, a lot of resources, and this makes the things very hard and not efficient, right? This is not efficient to do those things. So that day, initially in the 80s and 90s, we used to use the OPAMP, all those things, OPAMPs, right? These are the representation of OPAMPs, operation amplifiers. So one commonly available OPAMP 741 IC, 74. So this is just an IC, although it looks like if you go to a market and buy 741, you told give me a 741, they'll give you a device like this with, I think there are 16 pins, 2, 3, 4, 8 this side, 8 this side. I don't know exactly. Maybe okay, not 16, 8 pins. 1, 2, 3, 4, 5, 6, 7, 8. This is smallest available. There are other ICs. You have multiple op-amps within it, but 741 is the most commonly used and most famous. Right. So it has some input pins. You can give input. Say we have V1 and V2 inputs, and it has also V out pin output. Right. And it has to be given some supply voltage, plus 12, minus 12, something, whatever. So these are the op-amp. I'm just giving a top view. What is op-amp we are discussing, and why we go for this analog processing? Because it is fast. Why fast? Because let's see, we have an input. Say we have input right now. So here I am giving some input. Directly it goes to inside the operational amplifier, and there are some transistors, some pair of 3, 4, 10 transistors. Really, there are dozens of transistors, but this transistor will be directly working on this input and will be giving me directly the real-time output. We don't need in between ADCs or DSCs for this processing, and we don't need a powerful DSP process, which is power consumption, very power consuming. We have few transistors required. You know, a typical DSP has millions of transistors inside it. So all this transistor will have consume a lot of power. They'll have a lot of delays. They have a lot of resource wastages, etc. And even the ADCs, DSCs are also not so simple devices. They have analog and digital parts within them. So you can see op-amp for simple processing like addition, subtraction, division. Op-amps are the best solution because it is fast, it is less power consuming, less resource utilization, and maximizing my design time also. Right? These all things get very complicated actually. ADC, if you go for complications, more complications like we need to how many bit speed of the ADC, how many bits I need to couple, what is the communication speed, what is the all these delays in between you have to manage, and a lot of programming, DSP programming or another important thing. But here we don't need anything, we just give the input and we get the output, right? Proper connections we give, that's it. Everything is analog. So things are much simpler in analog because it's directly, we are focused on single application, and we don't need any other devices or gadgets or programming or troubleshooting extra things. But the only thing in analog is design challenges are the trade-offs. We already discussed. There is always a trade-off in analog, right? Gain bandwidth. One example is gain bandwidth product. Gain bandwidth. We'll just go in next. Gain bandwidth. So what do you mean by gain bandwidth? So gain bandwidth product. So what it means is I'm plotting the gain versus the frequency. For example, this is the gain I call AV, voltage gain of a analog device or any device in general, and I have frequency of operation of the device. So I can see when the frequency range is less, my gain is maximum. But as my gain is reducing or frequency of operation is increasing, my gain is also reducing. So that means we are facing a trade-off here or a challenge here. So we have a high gain in some circuit. We have high gain. What happens? Your bandwidth is very less. So what is bandwidth? Bandwidth is the range of frequency. For example, this is zero frequency. This is F1 frequency. So this is the bandwidth is from here to here. So my bandwidth is very less than the amount or the different levels of frequencies my circuit or the system can handle is very less. So bandwidth is very less here, but my gain is very high. Right. So if I try to reduce my gain, I may reduce my gain a bit, but I may increase my bandwidth. Definitely, my bandwidth has been increased to a bit better. So if I go on reducing the gain maximum, my bandwidth is going to extend definitely, but my gain is suffering. Okay. So there is always a trade-off in. So this is called trade-off. Not only this, there is another. Now we are also concerned about gain and frequency. We are also concerned about power dissipation, how much power my device is consuming, and there is voltage swing. Voltage swing is another important consideration. I need very good voltage swing, right? We need to represent some analog output. We need very good voltage swing. This means minimum voltage is 1 volt, maximum is 4 volts. Swing is 4 - 1 3 volt, right? Our voltage swing is going on reducing. That means it's very difficult. This we have seen in the common emitter amplifier load line. If your load, the Q point or operating point is nearer to cutoff point, nearer to saturation point, yeah, we will face this problems of voltage swing. Okay, so this is analog. We have trade-off, gain, bandwidth, power, voltage swing, etc., etc. All of those things. But the most important part is op-amps were designed for much faster operations. Op-amps were designed for easy, easy design. We have need an adder or subtractor. So what is op-amp actually? Operation amplifier is nothing but a lot of transistor. It consists of a lot of transistor packaged or fabricated to in a chip IC. What is IC? In the integrated circuit. Integrated circuit. IC is integrated circuit. So it looks like this. You might have seen, we have discussed already. This is the chip integrated circuit. This is a one silicon wafer. Inside which there are a lot of transistors, maybe 20, 30, 100, or even thousands. Even digital ICs have a lot of, even DSPs also IC, your microprocessor, smartphone processors, RAM. Sorry, not RAM. RAMs are also chips, but the RAMs are also chip. Your processor, Snapdragon, i3, i7, Intel, i3, i7, AMD, all those comes in chip. But these are digital chips which have billions of transistors. But analog chips are also having a lot of transistor, but may not be billions, right? But so what is inside the chip? You should know that there are a lot of transistor working as a resistant capacitance and all those things. Although we'll try to reduce resistance capacitance within the chip, or because of inductor, definitely we are not looking to forward for inductor because of a lot of problems, power dissipation, delay, etc., etc. So all this transistor fabricated within a single silicon wafer, I will package as a chip, right? And I will give the terminals. This is input, output. This is output. This is this is VDD, or we have some negative supply voltage, V in, V1, V2, and V out, something like this. And we have some other pins also of offset and error correction. All those things will be there. Okay, so basically you should understand that in IC chip, in op-amp IC, for example, 741, we have a lot of transistors within them. So they are connected together, because humanly, if you try to design these things in a breadboard or in a circuit PCB, there's a lot of difficulty. We have to troubleshoot a lot of transistors, 1, 2, 3, 4. So it's not easy to design, troubleshoot. If some slight mistake or slight problems happen, it will not work properly. Because the more number of transistors, the more complications in digital analog. But in digital, there are a lot of software tools which help us in for fast fabrication, right? But analog, the tools are not there right now. Also, designers has to design transistor by individually 1, 2, 3 like that within the chip, right? So it is not easy to design or keep a lot of transistor within a single circuit because of the lack of time, complications, troubleshooting problems. And another problem is if you connect using outside PCB or a breadboard, the length of wire also matters these days. Well, wire length is very high. It acts an antenna, right? Antenna. You might have written communication antenna. If antenna, the frequency you're transmitting is f, the antenna length is lambda by 4 something. I think you discussed this thing, right? So we have all the wires in your circuit will act as an antenna. So what is the net effect? If the wires in your circuit act as an antenna, there will be having a lot of noises. Electromagnetic signal will be attacking them, and a lot of noises will come. So we have a lot of frequencies around us: 5G, 4G, Wi-Fi, Bluetooth. There are different frequencies. So this will act as a noise in your, and this also directly proportional length of the wire. The wire length is very high. It acts as a it acts as a absorption point for the radiation, so different frequencies. So these are some of the points which make us think like, let us go for IC chips in analog also. So that is much easier. It's also we can buy directly We can directly buy those from markets and directly use for all those applications, right? So all these are general purpose. All these possible chips we discuss here is general purpose chips. General purpose chips. General purpose. So because sign for an OPAMP can be used for lot many things. Can be of all the operations which you discussed. Can be a lot of applications, projects, amplifier, any kind of gain, any gain amplifier, any kind of thing. So this is general purpose. The specific ICs are also there. For example, ADCs are some specific ICs, or you can see in your smartphone or a television or your some toys. You can see some chips which are specific. That's not general purpose. There's specific purpose, but usually you can see 741 also inside them. But big companies who can develop their own chips, they'll try to develop their own chips. Fine. So before going to the OPAM, I want to discuss one more thing with you. So we have this lot of amplifiers connected back to back. This is one amplifier. This is another amplifier. So forth. A lot of amplifiers connected. Right. So this amplifier have a gain, say for example G1. This has a gain G2, gain G3, G4. So I have an input here, V in. So I have an output here. So what will be my ratio? What is the total gain? I have a gain here. This is intermediate output, V1 dash, VO dash. This is VO double dash, VO double dash, something like this. So we can know what is gain. Gain means ratio of output by input, VO dash by VI. We have G1, and we have V double dash by VO equal to G2, and likewise we have VO double dash by VO double dash equal to G3, and so forth. We have VO double by VO double dash equal to G4. So what is the effective gain? Effective gain means V output divided by V input. You can see if I multiply by this, all these things multiply together, what I'll get? If I multiply all these things, this G1 into G2, G1 into G2 into G3 into G4. We can say this is cancelled by this, and this will be cancelled by this, and this will be cancelled by this. So net effect we have V output by V is equal to G1 into G2 into G3 into G4. So this is the net gain of the system, right? So this is the net gain of the system, right? So when you have a lot of amplifiers connected in sequence, the total gain of the system, the net system, this is the system. The net total gain of system is multiplication of those gain, individual gains, G1 into G2 into so forth. G1 into G2 into G3, so forth. Okay, so we have to multiply. So now the next point is we can multiply. That is okay. That is not a big issue. But the problem here is all these amplifiers. We know amplifier gains are very high. We have a lot of big amplifiers, and the gains are 10 to this amplifier gain is 10 raised to 6. This is 10 raised to 8. This is 10 raised to 6 again. This is 10 raised to 4. Okay, so how will we calculate this gain of net thing? This is V output divided by V input. So what we'll do, we calculate the V output by V in. Nothing but we know this total gain is the multiplication of all this gain. So we'll multiply 10 raised to 6 into 10 raised to 8 into 10 raised to 6 again into 10 raised to 4 something, and we started adding how much? 10 raised to 6 plus 8, 14 plus 6, 20, 24, something like 24. So this is a big number. So to avoid this, because when we deal with amplifier, we are always dealing with very high gains. We are always dealing with very high gains in the power of 10 raised to 6, 10 raised to 8, 10 raised to 6, again 10 raised to 4. So what we'll do, we'll think like anyway we have to add this exponentials of the 10th, exponential of the 10, right? So let us take log of all those things. Let us take log to the base. So let me express the gain of an amplifier in terms of dBs, right? So I call this gain of this amplifier is say 6. I can express in 60 dB or something like that. So if I express in dB, this is 80 dB. 60 something we can. So what will happen if you take the log of these things, log 10? So if I take log of all those things, log to the base 10, 10 raised to 6. Now the multiplication, the complicated multiplication is converted to addition. So this we have log 6 into log to the base 10, 10 raised to 8, and so on and so forth. So what happens now? I just need to add this add this dBs or add this coefficient because I'm taking log, right? So we can see that is why we, instead of multiplying these big numbers, we convert these gains into decibels, decibels, right? Decibels. So this 10 raised to 8 can be considered as 80 decibels, something like that. So we convert into log based. So we add, instead of multiplying all this different gains, it's easier for us to add the decibels, gains in decibels. So it's much easier. This is maybe 40 dB, this is 30 dB, this is 100 dB or whatever. So we can just add, the net gain is 170 dB, just adding all those gains. Okay, so we express this amplifier gains in decibels because of this reason. Instead of using big numbers, 10 raised to 6, 5 into 10 raised to 23 or 10 or whatever. So this is much difficult. So better to have a simplified logarithmic. We can add those gains. So if I add a new amplifier here, I am just concerned what is a dB, 20 dB. So this net is equals to 20 dB. It's much easier. So total is 190 dB, something like this. So this is much simpler um, for the calculation in terms of amplification. Okay, so that's about dBs, and now we'll come back to the OPAMP. Now, why we design OPAMP? We have a lot of operations to perform. So what are the features which we expect in operational amplifier? So this is an amplifier OPAMP. We call this as operation amplifier. Okay, so what are the features we expect the OPAMP to have? Now let's see what are the features. OPAMP, operation amplifier. Okay, anyway, it's an amplifier, so I need a very good gain, right? We need a very good gain. So that is one of the important factors. First thing is my gain should be very high. I need a good gain. Gain should be very good. So that is the purpose of using an amplifier. Amplifying. So gain. So what are the next thing? If I give a small minute signal, so I should have a very good amplification in the output. Okay. So amplification. Now what else? Yeah, bandwidth. We are discussing about the gain bandwidth product. So we need a good bandwidth also. Bandwidth. So what is defined? How we define bandwidth? Bandwidth is a range of frequencies which a system or a circuit can process. For example, my circuit can process from 10 hertz to 10 raised to 8 hertz. That means your frequency is bandwidth is, this is F1, this is F2. Your bandwidth, or that means the circuit can operate between F2 minus F1. That is nothing but approximately 10 raised to 8. That is, 100 megahertz is the bandwidth approximately, right? Something like this. This is the bandwidth. So bandwidth also should be very high. Gain should be high. Bandwidth should be high. Now, what about the third important point which we discuss in amplifier? Yes, what about the resistance, input impedance? Input impedance should be also very high, right? We need very high input impedance. And output impedance? Output impedance also should be very low, right? So what are any other things I require? Gain very high, bandwidth also, noise also I need noise also should have less noise also. But anyway, so I call this noise, the another term common mode rejection ratio, something. So also will be good, should be good. Or you can say noise effect should be less. Okay, something. These are a few examples, but I'm just saying. These are things which I require. I want my amplifier or op-amp to have possess these all things. Okay. So ideally, now I'm going to ideal and non-ideal. Ideally, what I want. Ideally, I want gain to be infinity. Bandwidth also should be infinity, because my op-amp should process frequency without any limit, right? So infinite gain and bandwidth also should be infinity. Input impedance infinity, and definitely input infinity. Output impedance should be 0. We have discussed. You don't need the signal, amplifier signal to loss, so definitely should be 0. And CMRR and noise, I don't say CMRR. Common mode rejection ratio also should be very high or infinity. This is CMRR, common mode rejection ratio. It's like you are rejecting the noise. So this is a factor, although we don't discuss what is this. And so this is something noise factor. Common mode rejection ratio. We are trying to reject the noise kind of thing. So noise elimination should be maximum. So these are things are ideal factors, and practically let's see what are the practical values of this things in a common op amp. So in common op amp, gain will be very high. This will be around 10 raised to 6 to 10 raised to 8. This will be a very good gain ideally. 10 raised to 6 to 10 raised to 8. Bandwidth also should be very high, even 10 raised to 8 hertz, in that range. Right, very high bandwidth also. Impedance should be very high, 10 raised to 8, very high. Output impedance should be 5 to 10 ohm, very less, not zero, but there is always some slight impedance. CMR also, right? Let's not discuss. It's fine. So these are the things which you expect in your idea of an operation amplifier. Then is high gain, high bandwidth, input impedance is very high, output impedance is low, and noise elimination should also be very high. Okay. I hope this is clear. What are the ideal features? Ideally, all this maximization should be very infinity, and minimization, all those things should minimize, should be zero. Noise also should be completely eliminated ideally. Okay, now let's see how an op amp works. So I don't go for internal circuit of op amp. I just, this can, you can understand better as black box. Black box, you should understand this is a black box, and we are giving something, it is giving you some output. So that is a better way of understanding op amp in this course. Okay, so we should know this is a lot of circuits inside the black box, lot of transistors, lot of wires, connector, intermittent power sources, and all those things. We need to give a plus 12 or minus 12 voltage, and whatever input we get, we'll get a good what we expect. It can be amplified, can be filtered, can be integrated, differentiated, adder, voltage, average, whatever. Okay, so this is, we are considering as a black box. Now let's see, there are terminals of op amp. There are main terminals of op amp are V1, V, or we can say V plus, V plus, V minus, and we have V output terminal, V out. And now definitely we have plus 12 or plus VCC, you can say plus VCC, and now we have minus VCC. This is most important pins of a 741 op amp operation amplifier. Now, what are the difference between plus V in and minus V in? That is a very good, very important thing. You should note it. This we already know, plus VCC and minus VCC. So what is plus VCC? It's just a positive supply voltage. Positive supply voltage plus 5 volt, plus 15 volt. This is minus negative supply voltage, minus, right? Either there's option. Sometimes you have to put, can be zero also, it can be grounded also, no problem. Still works. Okay, what about this? This plus indicates this input is called non-inverting input. Non-inverting. And what about this minus? So this input is called inverting input. Inverting input of an op amp. Inverting input and non-inverting input. Okay. Now, what do you mean by inverting and non-inverting input? If you give some input in the non-inverting point, if you give some input in the non-inverting point, you can see output will be whatever we want, amplified and all those things, but you can see the peak. It's not inverted. The phase, there is no phase difference, right? It's not inverting. The output is VI, and input is VI, output is gain times VI, right? But the same thing if we give in non-inverting, in inverting input, what will happen? In the inverting input, the same thing will be reversed. If we give this input in the inverting terminal, the output will be amplified but reverse. You can see the reverse. This is a positive was initially, right now it is reverse. So I call this is somewhat like approximately minus gain times input voltage VI. This is VI. Okay, so this is the difference between inverting and non-inverting input of an op amp. If you give input towards one terminal, it will be amplified, but the same phase. The phase will not be changed. Phase different. You can say phi equal to 0 degree in the first case, non-inverting case. And second case, we can say phi is nothing but 180 degree, plus or minus 180 degree. 180 phase shift is there, right? So this is reversing. So that is called inverting input of an op-amp. I think this is clear. There are inverting input, non-inverting input, 2 pins. Now, um, now let's discuss different connections of an op-amp. So what is actually op-amp? What is happening inside op-amp? You know that inside op-amp, you already know there are a lot of transistors that you know. But what is actually the transistors are doing? Is it a common emitter amplifier, common base amplifier, or common collector? What is this happening? So that if you someone asks this questions to you, or you ask someone this questions, the answer is right now I don't know. I know it's a black box. There is some kind of things happening inside the op-amp, but right now I'm not aware. But if you go to some interview after your BTech, they will ask the same thing. Now you have to answer. So right now, then you have to answer that inside the op-amp, there are different stages, Although these stages are I'm expressing as block diagram, these are actually transistor circuits. So input is a differential amplifier. Differential amplifier. What is differential amplifier? As the name states, whatever I input into the differential amplifier, this is one input, this is V1, V2. Now what happens? The differential amplifier will be amplifying the difference. That means the output of the differential amplifier, what will be the output here? Different V1 minus V2 into amplified into gain. This is a differential amplifier, right? Then what happens? After the differential amplifier, we have more gain stages. What is the meaning of this? Nothing. It just means that we have amplifying that this output we got from the first stage. We are again amplifying more amplification, more amplifiers, more different types of amplifiers. Now there is an output last block. This is some, we can say this is impedance matching circuits. Impedance matching. You can say collector, common collector something, common collector amplifier. So this is basically, to give you a zero resistance, zero output resistance. We need zero output. So we have different blocks. One is differential amplifier. Is again more amplification. We are putting more amplified voltage, or we are amplifying that differential gain stage again and again. Then we have output stage, output like which has less resistance, kind of thing. Okay, so this is my internal diagram of my op-amp. So basically, you should know there's a difference. So now you may ask, what is the meaning of differential amplifier? Although, if you want to know, we can refer Malvino. There is one chapter on differential amplifier before going into op-amp. Malvino discusses the differential amplifier. But in our discussion to understand op-amp, we don't need to understand the differential amplifier. I'll give a small example of differential amplifier. This is say plus 5 volt, and I'm giving small input voltage here. So this is R. Now, as the voltage at this point, now at the voltage is the point is rising. Let's take the positive edge. So now the voltage at this point is rising. So what happens? The transistor, this voltage, the transistor base emitter voltage is increasing. That means transistor becoming more and more on. That means the current I will be increasing. So I can say at the voltage input, as the input voltage is increasing, the current or the say IC or whatever IC is also increasing. Right? This we know. We already know this curve. Right? What is happening when the IC is increasing? When IC is increasing, what about the output voltage? This output voltage is nothing but V out equal to VCC. That means 5 volt minus IC into RC. Right? This we everyone know. Everyone knows that V output voltage, V output, what will get in output? Kirchhoff law. Supply voltage minus drop across this resistance. We are dropping some voltage across this resistance. So if I subtract that drop, I'll get my output voltage. That means this is my output voltage. Voltage across the V out and the ground. Right. So this is equation is V out equal to 5 minus ICRC. Now what happens as the input is increasing? And the input is increasing. we can say that the input is increasing. As the input is increasing, you can say input is increasing, my IC is also increasing, my IC is also increasing. So when IC is increasing, we can say this whole thing, the drop across the resistance is increasing. When the drop across the resistance is increasing, your V output is reducing. Why? Because it is 5 minus the drop across ICRC. As IC is increasing, this drop is increasing. And that drop is increasing when V output is decreasing, right? So as my input is rising in the input of the transistor, and base emitter voltage is increasing, IC is increasing, and V output is reducing. So this is reducing. This node is getting pulled down because this pulled down, voltage is coming down, right? So this is increasing, voltage is coming down. Getting? So now I think you're getting more understanding what is happening. Now what I'm doing is I'm connecting one more. I'm keeping one transistor here. I'm connecting one more transistor pair like this. Same thing. And here I'll connect a current source. Right, this is a current source. I call I emitter side. This is a IE. Okay, so I emitter source. So again, we have two. Last time we had discussed only one block. Now we have two blocks. This you can say R1 or R2, and both are given to some same voltage. Like we have connected +5 last time, so +5 volt, or we should say VCC. This is VCC. Now what is the main important point here is I have two. Last time I took voltage output from here at this point. Now I have two outputs. This is V output 1. This is V output 2. Now V input 1 also I have. V input 2 also. Now I'll just tell you this circuit is called the differential amplifier. Now let's see what is differential amplifier acting. How it is acting. Okay, now let's see. I'm giving some input here. So as I discussed previously, as this input is increasing, this V output is decreasing. So what is happening? Why that is happening? We already discussed. Now because IC is increasing, we know this current, when this is increasing, this current IC or I1 is increasing, right? I1 is increasing. So what happened? This I1 is flowing through this point to the transistor inside, and it's coming through the ground here, to the ground. Now this current is increasing. That means initially there was a current. Now because of increase in input Vi, my current is increasing. But you can see here the IE is constant. This is a current source. Current source means you have constant current. You should remember the current source is constant. At the time load is increasing or time is increasing, the current is constant. This is I current source. IS is constant with respect to time or any load or whatever load. This should be constant. So this current source is always constant. So this delta I is flowing. So this should be some minus delta I. Minus delta I will be flowing through here. That is meaning. What is the meaning of minus delta I flowing? That means current in this branch will be reduced. Current in this branch will be reduced correspondingly. The more I increase the current in this branch will be reduced automatically, because this current source principle should be constant because of this current source. Okay, so what happens when the current of this branch is reducing? So what is net effect? We can say that when current this is reducing, when this current is reducing, the voltage drop across this resistance, what happens? This also reduces, because we know VO2 is also nothing but VCC minus I2 into R2. So what you are discussing, I2 is reducing, so this voltage is reducing. So what happens? This VO2 will be increasing. So you can say as VO1 is reducing, VO2 is increasing. So this is the case. I'm giving some input, I'm increasing my input, but my output is reducing. I'm saying it is inverting. Here it is inverting, but here it is non-inverting, right? But in opposite, my VO2 is increasing. So the net effect, what happened? If I take the difference, V output, if I consider difference about VO2 minus VO1, we can say this is the differential output. We are taking output from these 2 points, VO2 and VO1. Okay, so these are this is not for exam purpose. I'm just giving for your understanding. This is a differential operation. We have two different inputs, VI1 and VI2, and based on the input given to this individual different inputs, my VO1 and VO2 is going to vary. right? If I1 is increasing, VO1 is decreasing, but VO2 is increasing. But if V output I take from VO2, it will be increasing. The same output I'll take from VO1, it will be decreasing. So this is what happening inside the op-amp. Okay, so this I'll repeat again. We are discussing the differential stage. Inside the op-amp, there's a differential amplifier. So what is a differential amplifier? We have one resistance R1 and a NPN transistor connected, and then again there are two poles like that, and one current source is connected to the emitter side of both. What is the idea? When slight increase in current in one branch, it is compensated by the decrease in current in the other branch. So if there's a delta I plus here, it's a delta I minus here, so that the I is constant, right? Because I1 plus I2 equal to IE, right? If I1 increases, I2 should be balancing by decreasing. So by the balancing of this current, my voltage across these two terminals will be varying, right? If this is decreasing, this is going to be increasing, because basically there is voltage drop across this resistance R1 and R2 is going to decide my VO1 and VO2. Okay, so we have two output, VO2, VO1. If we take the difference, we got differential output, and we had two inputs also, VI1 and VI2. Okay, so this are the two input of your op-amp, VI1 and VI2. So if you want to understand this concepts more deeply, more comprehensively, you should follow Malvina or Volstead. But for exam point of view, I think this much is sufficient. This is called differential amplifier. You can write this as differential amplifier. D. This is a D, differential amplifier. So this is one of the main first stages of the op-amp. After differential amplifier, then after DFAM, we have other amplifier gain. We just improve the gain. Last stage is just coupling or output impedance or common collector stage. Common collector stage for matching the impedance to make the output impedance 0. So all these things can be combined into one single IC 741 op-amp IC. It has 8 pins. Okay, so that's about the happening inside the op-amp. Okay, so we again come back to our op-amp. What we know, this is your op-amp. There is one inverting and one non-inverting. So this I call it V minus. This is V plus. Okay, you should remember these things with respect to the last circuit we are seeing. So this is VO, V output. So you say there is no two output here, but you can say one output we are discarding, kind of. Okay, so let's see the let's say the equivalent circuit of an op-amp. Now there are two voltages going inside the op-amp, and both this will be connected inside the op-amp through a impedance, very high impedance. So you can say there is some very high impedance called Z input impedance of this op-amp, ZI. Okay, so input impedance is there. Now what about the output? Yes, output is also will coming, because whatever the input you're getting, here the input is across this resistance, Zeta is V1. For example, this is V1, this is V2. So I get V1 minus V2 is the drop across this Zeta. Now what is the output? Output is the amplified version of this V1 minus V2. So I have something in the output like this. This is Z output. This is Z output. So this is output impedance. This Z output should be ideally 0. Now what is this voltage? This is something generation. This is equivalent circuit. In equivalent circuit, we just represent the behavior or functionality. So this is a gain. Gain times the V1 minus V2. Gain times the input difference between input. Gain times a V1 minus V2. This is V1. This is V1 and this is V2 input. So difference is differential amplifier, make the difference V1 minus V2, and there's a gain stages will give my more gains A into V1 minus V2. So output is same thing. Output is this thing. Output is gain into V1 minus V2. Also we have some drop across this thing. Ideally should be 0. So this will be my output. Okay. So this is about the internal diagram of op-amp. That means there is an input V1, another input V2, and this will be drop across Z1 input impedance, and output this will be amplified and given in the output V0. Okay, so this is your net representation, behavioral functional representation of the OPAMP. Okay, now so let's analyze some of the circuits of applications of OPAMP. Now, before that, I will discuss one important concept: virtual ground. Virtual ground principle. Virtual ground principle. Okay, this is very important because whenever you talk of op-amp, you're thinking of solving some circuits, some amplifier circuits configuration with using op-amp. So you need this principle to solve most of the circuit finding. This is very simple, but you should know this. Okay, so what this principle says is we have an op-amp with input V1 and V2. Okay, and output is, it is VA into V1 minus V2. You know that. Okay, so I'll just write this A into V1 minus V2. Ideally, this is my output. Ideally. Why ideally? Because there is losses. Definitely, there is a series resistance output. I'll drop some voltage there, but ideally, I need this much, right? So something like this. So this is my output. Now, what is the gain? What is the gain? Gain of any amplifier, the ratio between output voltage and input voltage. So output voltage, here is A into V1 minus V2. And input voltage, definitely we know the two input voltage you are applying V1 and minus V2. So this is the gain, right? Or we can say the gain, gain is the ratio of output to the input, right? So this is clear. Okay, now we'll come to the gain. What will be ideally? What should be ideally? What should be the gain of the amplifier? Ideally, we are discussed. Ideally, we want the amplifier to have a very high gain or infinite gain. So we say yes, we definitely want the amplifier to infinite gain because this is a human nature. We want everything in excess. So we want everything infinity, unlimited happiness, unlimited money, unlimited joy, everything. So we want infinite gain always. So there is no compromise. So what we will do? So as ideally, we are asking this A is infinity. A is infinity, right? Okay, that means V out divided by V in equal to infinity. That is nothing but the gain. You're telling gain is infinity. That means V out by V in is infinity. That means what's the meaning of that thing? So that is V out divided by what is V in? V1 minus V2. This is equal to infinity. So what is the meaning of this? Now you just consider this statement, this expression which I have drawn or which I have written here. Now what is the inference from this? If something needs to be infinity, if something should be infinity, that is very high value, what should be the either the numerator should be very high or the denominator should be 0, right? So at least this high value V out should be very high value. That is also fine, but we are not much interested in processing very high values because that is can be very high. We don't care about those very high values. So what we are considering V1 minus V2. That means if we are approximating or assuming high gain, that means V1 minus V2 equal to 0. That means V1 equal to V2. We can say messages. Yes, V1 equal to V2. Right. So what is the meaning of that is here? Here that means if any voltage I give in the into the op-amp, you can see this V1 equal to V2. That means these two voltages are can be assumed to be equal. That means we can assume that there is something connecting these 2 points, input to the input of this op-amp, making them same potential, same voltage potential, same potential. right? And we know one more thing. We know one more thing. That means we cannot we cannot push any current into these terminals. I can be zero. Why? Because z input is assumed to be infinity. Again, here also there is no current is going to be inside the op-amp because this very infinity input impedance is assumed to be infinity, right? At this point we can say whatever v1 is a potential, v2 will be the same as the potential. Okay, so this principle is very helpful in solving problems. If you assume v1 equal to v2, because usually one of these terminals will be grounded, we will not be using two v1 and v2 at the same time. In most of the applications, there are applications where I will give v1 and v2 in both cases or simultaneously. For example, comparator, we have to give v1 and v2 same time, but no, most of the cases we won't give v1 and v2 at the same time. So at this time one of this will be grounded. So it is very easy to analyze the circuit because of the virtual ground principle, right? Now let's start. If you understand this virtual ground principle, we can start analyzing some simple circuits. So I'll repeat what we are discussing. This is very important. So the main point I discussed is virtual ground principle. We assume that the gain of the op-amp is infinity. That means V out by V in is infinity. So output is gain times V1 minus V2. Input is V1 minus V2. This is two input data. So output gain should be infinity. So V1 V out by V in should be infinity. V1 is V1 minus V2. So this should be infinity means V1 equal to V2. So that means V1 and V2 are in same potential. This is called virtual ground principle, right? So we assume that V1 and V2 have same potential. Although virtually we assume this is short circuit. Virtually this is short circuit. Virtually this is short circuit, short circuit, virtually short circuit. So this is called virtual ground principle. It's called virtual ground principle. Okay, so let's see. So let's try to analyze some simple circuits, minus, plus. So let's give one voltage V1 and I give some resistance here. Now before that, now you understood virtual ground principle. Before that, let me give some. So I'll give some V1 voltage here. Okay, so voltage here, another V2 voltage. Okay, now let's I give a V1 equal to, say this is sine wave in V1. This is say slight small voltage, 2 millivolt voltage, 2 milli plus 2 millivolt. This is minus 2 millivolt. Now I have V2 I'm just putting, or V2 also I'm giving slight voltage. Maybe I'm giving 3 voltage, 3 millivolt, 3 millivolt plus minus 3 millivolt minus. Okay. These are with respect to time, my waveform. These are my waveforms with respect to time. Now let's see what is the output. Okay, say assume that you have gain of 100. Let us assume that we have a gain of 100 or 1000. Gain A equal to 1000. So what will be output? The output is V out equal to gain into V1 minus V2. Right. One more thing I should tell you that the frequencies are same. This is frequency 50 hertz. This frequency is also 50 hertz. So all those ideal things I'm keeping and I'm calculating the output. This 1000 into V1 minus V2. What is V1? 2 millivolt. 2 milli minus 3 millivolt. Right. So we have 2 milli minus 3 minus 1 millivolt here. Minus 1 milli into 1000. That is minus 1 volt in the output. Okay, is it clear? We have a gain of 1000 and here we can say two voltages V1, that is 2 millivolt plus and minus sine wave. V2 is also 3 millivolt plus and minus. Okay, so I have a gain of 1000. So gain times difference between input V1 minus V2. Okay, now we can say if V2 is high, can from this you can say, can see that if V2 was a higher voltage, if V2 was high, I'm getting a negative voltage. Now let's see if V1 is high, what we'll get. Now, if instead of this, if I increase my V1 to 5 millivolt, same frequency, but this is 5 millivolt, 5 millivolt plus, okay, this is 5 millivolt, this is minus 5 millivolt. Frequency remains same. So this is, I mean, increasing my V1. So this is becoming 5 millivolt. This is becoming 3 millivolt. Okay, now let's see what is output. V output equal to gain times 1000 into V1 minus V2. 5 millivolt minus 3 millivolt. So we got 1000 into 2 millivolt. That is 2 volt. Now here is plus. Now we can see a property here. Whenever my V1 is greater than V2, I have a positive voltage. Whenever my V2 is greater than V1, I have a negative voltage in the output. Right? So the pulse is like this, something like this. Negative, it is something like this. There is a phase difference. So basically, this is acting as a comparator, right? So even if you can give even DC voltage also, it's no problem. Even if this is a constant DC of say 2 millivolt, this is a constant DC of 1 millivolt. So here we can say V2 is smaller, V1 is greater. So output is V output is equal to 1000 times V1 minus V2. This is 2 millivolt minus 1 millivolt. That is 2 minus 1, 1. That is 1 volt. So still it is positive. So we can see whenever V input is greater than V output, we have a positive voltage. Whenever V2 is greater than V in, we have a negative voltage. So this is a best example for comparator. This is one example where we can compare my inputs V1 and V2. So OPAMP can be also used as a comparator, right? Yeah, just because it's different, they taking the difference, and the output is a high voltage. We know that V1 is greater, output is low voltage, V2 is greater, or vice versa. Can be reverse also, right? So this is one example of OPAMP as a comparator. This is, so I'll name this as a comparator operation. Comparator. Now let's come to the real. This is an ideal thing which we discussed. What happens in the real life? Let's see what happens in the real life. Now this is minus, this is plus. Here also I have V1, V2, I have V output. Okay, now let me show you same one. I'm giving the same voltage, same one. Let this is be 3 millivolt. Same way. This is be let this be 1 millivolt, or we can say 2 millivolt also. Frequency we can say. Okay. Now what about the output here? We know output is gain times V1 minus V2. That is what we have discussed. Now what is a gain? We know gain should be infinity, but in a practical op-amp, the gain is very high, not infinity, but it's very high, like 10 raised to 8. Can I say 10 raised to 8 gain is normal for an op-amp? Let's see now. Let's put this 10 raised to 8 into V1 minus V2. So what is V1 minus V2? That is 10 raised to 8 into V1 is 3 millivolt minus 2 millivolt. Let's see what is output. That means 10 raised to 8 into 1 millivolt. That is nothing but 10 raised to 5 volt. So what is the meaning of 10 raised to 5 volt? That is 1 lakh. 1 lakh voltages is coming in the output. Now what is the problem here? Who can tell me? Is it practical? We are getting a 1 lakh voltage using a op-amp. So we always were discussing, is the amplifier some ideal device which can amplify any voltage? Right? So let's see. This is the input. This is, yeah, what is the difference? V1 minus V2. You can say V1 minus V2. What will be the waveform of a V1 minus V2? This is a V1. This is V1. This is V2. V1 minus V2 will be like this, simple V1 minus. This is V1. This is V2. This is V1 minus V2. And the output amplitude we got 10 lakh. So that means the waveform will be very high amplitude, very high amplitude. We cannot describe here. This is like 10 raised to 5 in the positive direction and 10 raised to 5 in the negative direction. So this is my output, right? That means this much times this 10,000 volt is the output amplitude. So this is not actually, it is not feasible to see, or because whatever voltage I'm showing in the output should be given, cannot be cannot be greater than my VCC. That means plus VCC I apply to the op-amp, and minus VCC I apply the op-amp. So this VCC and V minus VCC or plus VCC is the maximum voltage that I can see in the outputs. Again, I will invite your attention. I'll just want to make you remember that when we draw the load line, or you can see the maximum possible current and maximum possible voltage is limited. This is VCC. This is VCC, right? This is the maximum possible voltages the circuit can, or your output device can give. So this 10 raised to 5 volt is not possible, because this is always limited by my circuit is always limited by my VCC and minus VCC. So what happened? This will be cut like this. This is VCC, so we cannot show in output more than this voltage. So this is whatever VCC plus 12, this is plus 12. And we cannot show more voltage or more waveform more than minus VCC, this is minus 12. So this is called saturation. Getting? That means your op-amp wanted to show high, but it is not able to show because of saturation. So saturation, it's already saturated. Saturation. Because this maximum possible is plus 12, minimum possible is minus 12. So I cannot show more than this is not possible to show. So we can say this already in saturation. So output is a square wave. Yes, you'll be surprised. Yeah, input is a sine wave, and V1 minus V2 is also a sine wave, but I'm seeing a square wave in my output. Why? Because your real sine wave cannot be shown by your op-amp because it is in saturation. Because our maximum VCC biasing voltage we give is plus or minus 12 or 15, like that. Okay, so this is one thing practically, because the gain. Why this happened? Because the gain is very high in op-amp. So even a small voltage is highly amplified, and you'll get some sine wave in the output. But actually, this is not a sine wave; it is saturated voltage of some big sine wave. Okay, I think you're getting what I'm saying. Okay, so maybe it is a nanovolt. The input is V1 minus V2 is say 5 nanovolt. Then let's see, output is V out equal to 10 raised to 8 into 5 nanovolt. Now let's see, it is possible to represent this. Nano means 10 raised to minus 9, right? Minus 9 and this 8, this is 0.5. Then we get 0.5. Oh, now it is possible. This 0.5 voltage can be shown in the output because the input is so small. Instead of milli, I'm showing you 5 nanovolt. So basically, even your input is in micro or nano, then we can, op-amp can definitely amplify. Still, there's a possibility of saturation. Now we can try with microvolt. If this is in 1 microvolt as input, still my output will go to saturation, right? Why? Microvolt into 10 raised to 8. Definitely it been 100. 10 raised to minus 6 into 10 raised to 8, 100 voltage, right? So that is also not possible to show even microvolt difference. Still it will go in saturation. So you should understand what is saturation, and because of the heavy gain, you won't see the complete waveform. You'll see till that point your VCC can't show you. Okay, so I think we'll discuss some circuit and we'll stop it here. Okay, so first we'll discuss a simple circuit. This is I'm giving some resistance V1 input, and I'm just giving a resistance R1, and I'm just grounding my V2 or non-inverting terminal. This is actually V plus non-inverting terminal. This is inverting terminal V minus. Now what I'm giving is I'm giving a feedback system. Now this things becomes all the circuit of op-amp will give a feedback to stabilize the output. Let's see, this is a feedback resistance RF. Now this is V output resistance, V output voltage. Now let's apply the virtual ground principle. In any circuit is much easier. This is grounded. This is grounded. That means what is mean of grounded? This is grounded means this input is completely grounded, 0 volt here. So according to virtual ground principle, this also should be virtually 0 volt. This also should be 0 volt, right? Now let's see, calculate the current. Now let's calculate the current equation, so that we get the we are interested in calculate the expression of the output voltage, right, with respect to V in. Now we'll assume a current I1, And this current, can it go to this inside the op amp? No, it cannot go because of the input in infinite input impedance. It cannot go inside the op amp because Z input is equal to infinity. So there is I equal to 0 to the inside, no entry here. So what happens to the current? It cannot go to the ground also because there is no physical connection. There is no physical connection in virtual ground. So it has to go to the feedback path. The current has to go to the feedback path. So feedback resistance, and it coming to the IF, right? So it is coming to the IF and it's going to the output. Getting, because of input infinite input impedance, my current will be going to the feedback path, right? Feedback resistance R. Now let's draw the Kirchhoff equation. So what about V1? V1, we can say this is grounded. So this point we can write that V1 equal to I1 into R1 because of the virtual ground principle, right? Now what about V output? This is grounded. So again, we can take a Kirchhoff law from the output side to the input side. So we know this is a Kirchhoff law from the V0 here. That means V output is here. So Kirchhoff law applicable here also. Here we can say Kirchhoff law to the ground. That means V output equal to, V output current direction is towards the voltage source. That means I minus IF into R. Current direction is coming towards. Usually voltage has to pump the current in the opposite direction, right? But here the current direction opposite. So I had to write minus I, right? So now one important thing, what is I1? We know I1 equal to IF, right? I1 equal to IF because of infinite input impedance of the op amp, the current input or pumped by the V1 is going to the feedback path. I1 equal to IF. So we can write from this two equation. From these two equations, we can combine these two equations. We can combine these two equations to write that IF V1 equal to I1 into R1 and V output equal to minus I1 into RF. Okay, this can be 1, this can be 2. So now let's take the ratio 2 divided by 1. So that is V output divided by V input is nothing but minus R feedback divided by R1. So this is my output input relationship. Okay. So this configuration is called inverting configuration, inverting amplifier, inverting amplifier. Inverting, why? Because of this minus sign, inverting amplifier. This is called the inverting amplifier configuration. Okay, there are a lot of applications of this inverting configuration. I think it will be too much for today. So I think we can stop it here. So any doubts I can take. So one more application of this inverting is we can have multiple voltages. Instead of V1 here, we can have V2, another voltage connected to this point, V3, another voltage, the resistance at the same point, and V4. So all those things can be done. So output will be somehow using superposition principle. We can consider all these voltage sources individually and find the output individually and add all those output together. We'll get the net output or the overall output using superposition principle. So if we have multiple voltages, V output divided by V input. But here we have multiple inputs, so we have to consider individually. V1 equal to minus Rf by R1, or we can say V output equal to Rf by R1 into V1 minus, right? Plus minus Rf divided by R2 into V2 plus minus Rf by R3 into V3, provided this resistance are R2, R3, R3, R4, so on. So that these things we'll discuss next day or tomorrow. So you can put your any doubts you can ask. You can put your roll number in the chat.